Hey, it's Mr. Jarrett. I'm going to go over a few examples as to how to do scientific notation. And we've talked before about the pretty simple steps, which is first of all to identify where the decimal place is. Find out how many places you'd have to move it to change it to a number with one decimal, with one number in front of the decimal. That's between 1 and 9. And then finally write it as a being multiplied to a power of 10 or by a power of 10. That would demonstrate how many places you'd have to move it to put it back to standard notation. So what does that all mean? Let's take a pretty simple problem. The distance from the Earth to the Sun is about 93 million miles. Write this distance in scientific notation. So the first thing we want to do is obviously, let's recopy our number. So that number would be 93. Okay, so 93 million. And the first thing we need to do is identify where the decimal point is. And for those of you that are unaware, right now we don't see a decimal point. So if there's no decimal point, then where does the decimal point go? Well, it very simply would go right here. Because if you were to write this as money, then it would be $93 million. So that's where the decimal point would go. So we put our decimal point there. And then the second step is very simply to identify where it should go, so that it's a one-digit number between 1 and 9. Well, here's the one digit. You pretty much just look all the way to the end, and here's the one digit. So it would go between the 9 and the 3. So how many times you have to move it from where it is now to where it's supposed to be? You simply count it. 1, 2, 3, 4, 5, 6, 7. So you need to keep track of the fact that we had to move it 7 times. So the final answer then is just the product of rewriting it. So 9.3, we get rid of all these extra zeros because they're unnecessary, times 10 to the 7th power. And that's it. So in other words, the distance in scientific notation between the Earth and the Sun is 9.3 times 10 to the 7th miles. So let's do a few more of these. We're supposed to write each number in scientific notation. So the first one is 6,400 or 6,400. So again, write the number 6,400. There is no decimal point here. So the decimal point goes to the end, all the way to the right. And to make it a one-digit decimal, the decimal point should be here. So you had to move it 1, 2, 3 times. So you know that the final answer will be 6.4 times 10 to the 3rd. Number 4. This is 570, let's see, thousands, millions, billions. So 570 billion. So again, same process, 570, and there's 0, and then 1, 2, 3, 1, 2, 3, and 1, 2, 3. 1, 2, 3. And so again, no decimal point anywhere in the original number, so the decimal point goes all to the right. The decimal point needs to go between the 5 and the 7, so that 5 is the one-digit number. So to move it there, now we can get to another concept that shows pretty much anytime you get to a comma, there's 3. So here's 3, 6, 9, and then we can say 10 and 11. So we had to move it 11 times. So the final answer would be 5.7 times 10 to the 11th power. And then for number 5 is a word problem, but doesn't matter. A light year is the distance that light travels in a year and is equivalent to 9.461. Here we go again. Thousands, millions, billions, trillions. So this is 9.461 trillion kilometers. Write this distance in scientific notation. No problem. 461. And by the way, why do I rewrite the numbers every time? Because what you don't want to do is write on the original problem. And if you mess up, then you can't see what the original number was. Let's make sure we have 1, 2, 3 sets of zeros, 1, 2, 3 sets of zeros, 4, 6, 1, and 9. So it's very important to make sure we copy accurately. Again, no decimal, so decimal goes all the way to the end, and we see that we move it 3, 6, 9, 12 times. So 9.461 times 10 to the 12th power. So in each of these cases, it's written so that if we were to change it back to standard form, we'd have to move the decimal place 3 times to the right. Here, we'd have to move the decimal place 11 times to the right. And here, we'd have to move the decimal place 12 times to the right. So now, let's go in the other direction. If we're given a number in scientific notation and we want to convert it back to standard notation, what do we do? And this process is, in my opinion, easier than converting from scientific to standard because all the information that you need is actually given to you. It says here that you have 3.5 times 10 to the 6th. What you need to know is that the exponent is going to tell you exactly how many times to move the decimal place. So in this case, you'd have to move the decimal place 6 times. So let's rewrite the number first. 3.5 times 10 to the 6th power. And because this exponent being a 6, again, is positive, we're going to move it 6 times to the right. Because on a number line, if you have a number line, if here's 0, your positive number to the right and your negative numbers are to the left. So we have a very clear indicator of what to do. So we're supposed to move it 6 times to the right. So what does that look like? So 3.5, we're going to move it 6 times. So 1, that's around the 5. But now every other time that we move it, since there's nothing there, we have to add a 0 as a placeholder. So let's just put all the loops and then we'll add the zeros in. 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6 times. And so since the first time I moved it, I had to go around the 5, I needed to put 5 zeros for each of the other movements. So to clarify that, you can automatically know that since there's one number to the right of the decimal, I'm going to have to add 5 zeros before I even get started. So I know that it should be, my final answer should be 35 with 5 zeros. 1, 2, 3, 4, 5. So technically, you could have set this entire thing up in your head by knowing it's 35 with 5 zeros. Okay, so let's do a few more. 7.034 times 10 to the 9th. Again, we need to change it to standard notation by basically just following the exponent. So I'll do it at the bottom here. 7.034 times 10 to the 9th. This 9, the exponent, tells me move it 9 times to the right. Okay, excellent. So what do? We know the first 3 movements are going to take it around the rest of the decimal. So that means we should have 6 zeros at the end of this number. So 7.034, 1, 2, 3, 4, 5, 6, 7, 8, 9. And again, you put in your 6 zeros. And as you get more experience, eventually, like I said, you'll know that this should just be 7 point, I'm sorry, not 7 point. It should just be 7034 with 6 more zeros at the end. And that's it. So 7034 and 1, 2, 3, 4, 5, 6. So for our next one, it's 2.36 times 10 to the 5th. So same idea, 2.36 times 10 to the 5th is going to require that because we have to move it 5 times to the right, because it's a positive 5, the first 2 movements will take us around 36, so that's 2 of the movements, and there should be 3 more zeros at the end. So the answer very simply is 236 with 3 more zeros. And then finally, again, word problem doesn't mean anything. It's just a different way to represent the situation. The mass of one roosting colony of monarch butterflies in Mexico was estimated at 5 times 10 to the 6 grams. Write this mass in standard notation. No problem. The problem started with 5 times 10 to the 6th. We know we have to move it 6 times to the right because it's a positive 6. And so since every movement now, because this number is originally 5.0 because there's no decimal on the right, every movement is actually going to add a 0. So all you do is just add 6 zeros to the end of the 5. Because again, when there is no decimal, the decimal is to the right of the number. So 5.0, all 6 movements would require adding a 0. So that's it. We'll go over, in another video, we'll go over what to do if the exponent is negative, but it's pretty much the same idea. It's just that we're going to go on the opposite direction. So nothing to be concerned about, but go ahead and take a look at that second video to make sure that you are fully confident in what to do when you face scientific notation problems. Work well.